All right, we've got plane waves. All right, but so these are our solutions right here. Now, what we normally would want to do is the first step is once we got a solution, is step one would be normalize it. All right? But what did we say about functions that are normalizable? What must these functions do at infinity?
Go to zero.
They have to go to zero at some level. And then Griffiths argues faster than 1 over x, all right? Because if they don't go to zero when you go to infinity, you can't add everything up and have it equal to zero, the integral.
Right.
All right? So what's the problem with these things at infinity?
They don't go to zero.
These don't go to zero. If you use Euler's relation, these are sines and cosines.
Right.
Right? So do these functions go to zero at infinity?
No, they
No way. So do they have a shot at normalizing these? Not normalizable. So, not normalizable.
But then none of those three general solutions for the differential equation will be normalizable, would they? So it's not like we could pick another one and then...
Like what we did for here, for the infinite well, is we normalized them between 2 points.
Right.
Yeah.
But
Remember we said the wave function was
But
zero?
that's your boundary condition, setting up C1 and C2, but
Yeah.
how do you do that for this?
You can't normalize them. Okay? So you can't normalize them. And then there's another problem. Right? So that's one problem. So problems. Actually, I'll do these as problems. 1, not normalizable. 2, let's look at the velocity. Alright? So, when we look at the velocity of the wave, we kind of do it over here. The velocity, I'll label it like this. Velocity, quantum mechanical, equals, what do I have over here? Velocity equals omega over k. Alright, equals omega over k. And I'm lost for a second, so give me a second to get this back.
It's like lost in Q1.
So I'm lost for a second, guys.
In the book, it's on page 60, they say the velocity of the quantum is sort of e over 2m. And classical is...
Yeah, but I want to get that. So let me see if I can get it here. Yeah, I just want to get it here. So omega equals, so here we have En equals h bar omega. All right, and we had k equal to, we had it over here, equals the square root of 2m En over h bar squared, right? So we have omega equals En over h bar. So this is En over h bar, all divided by k.
There's an h bar that comes out of that. So it's En
Over by
over
k.
2m e sub n.
Oh, so check this out. So En equals k squared h bar squared over 2m. So this equals so guys, I'm fumbling here, and just to make sure I get this right. So k squared h bar squared over 2m. So that equals.
Did you just replace for K when you should replace for E? Yeah.
Yeah. So how did I do
I think if you could,
You substitute for omega and k in the original equation.
So what do I do?
Substitute in for omega and k, just like in the bottom, substitute for k.
Over here, put in for k?
yeah.
Yeah, the square root of, and then the
Okay.
square root
Yeah.
of cancel.
Okay, let's see if that goes anywhere. so this equals En over h bar, and then all divided by k, which is going to be the square root of 2m En over h bar. Yeah, thank you guys. Over h bar squared. So that equals En over h bar times the square root of h bar squared, all divided by 2m En. Yeah, this works. All right, and that equals, so if we bring this in here, it would be e squared over h squared, so that will cancel. It would equal the square root of En over 2m.
Here.
Okay? Sorry about that fumbling around, guys. V quantum mechanical. All right? So that's the so what is that, guys? Just to be clear, it's the quantum mechanical velocity, but the quantum mechanical velocity of what? Lamar, you just said, of the wave.
So why does that?
Okay? So what we're doing, we're showing all the problems with these solutions. The first problem is it's not normalizable, so it's not going to be a very good wave function for a particle, right? Yeah?
Why does the wave have to do with mass? Why is a mass involved in a wave velocity?
Same thing like a string.
Oh, it's like,
Yeah.
yeah, I get it.
Yeah. All right. So, but we're trying to point out the problems. Thank you, Bill. We're trying to point out the solutions. Okay, they're not so good. All right. Now, what is V classical? So this is quantum mechanical of the wave. So V classical, the particle.
dx/dt.
Particle is dx dt. All right. But it equals 1/2 mv squared. Right? Okay. Which equals v squared equals we have E total equals for a free particle, a classical free particle equals E total. Right? That's the total energy of a free particle.
Yep.
So we have V, so I should make it V. V equals the square root of E total times 2 over m, so V classical free particle. All right, so now let's do this. Let's look at V quantum mechanical over V classical particle. And equals the square root of En over 2m, all divided by the square root of 2e total over m, and that's going to equal 1 over the square root of 4, which is
1 over 2.
equals 1/2.
Wow.
Would you say Darling?
I said 1 over 2, but
Yeah.
That's completely like, what's the square root of 4?
Yeah, I said 1 over the square root of 4. So 1 over the square root of 4 is 1/2.
Oh, I'm thinking about it.
Oh yeah, I mean, you got to see it.
at first
So
I thought
how
it
does
was
this
square root
present
of
the
1.
problem, guys? How is this a dilemma if we just solve Schrodinger's equation for a free particle? First thing is our wave function is not normalizable. What's the second problem that we have?
The velocity is twice.
That the quantum mechanical velocity is half the velocity of our classical free particle. So shouldn't, at the level of quantum mechanics, that when we kind of get it to make a big particle, the correspondence principle, should it reduce to the classical velocity limit?
It
All right,
should.
and where are we? We're not there. Okay? So at the end of the day, what are we going to conclude about these free particle solutions?
They're wrong.
They don't represent free particle solutions at all.
They don't physically represent?
They can't represent a physical particle by themselves. All right?
Yeah, we could have 2 of them.
All right? But check this out. What we're going to do is this. And by the way, what energies do these have?
What energies?
Yeah, did we come up with a quantum number? Were there any restrictions on the boundary conditions so that we really had to use an En?
No.
So did we really
It was confusing.
restrict? to ENs with boundary conditions? And the answer is no, right? Right, it was with the boundary conditions on the ENs that we got the quantized level and the infinite well. So we have no such restrictions here. So what can the E's be?
Anything over.
So E's are free. E's equal free, continuous. All right? So here's what we're going to do, guys. All right? Is what we're going to do is we're going to say the size of x and t's of a real free particle, they're going to equal. Am I going to write down a summation? I'm going to write down an integral. All right? And then what I'm going to integrate over are the e to the I k x minus vt's plus e to the minus I k x plus vt's. All right? Because these are our basis set. Are these basis sets physical?
No.
Are they normalizable? Okay, no. All right, but but are they a good basis set in function space? Yes, because they came from separable solutions. So what I'm going to do is I'm going to multiply by this thing. All right, and so what does this become? Instead of our CNs, which were outright probability, CN squares were our probability. What is this thing?
Probability density.
This is a probability density. And what is it a probability per? It's a probability per k space. And what is k? Where k equals 2 pi over lambda. And then what am I going to integrate over? The k space. So essentially what I'm doing, and this is the end of the class, is what I'm going to do is, how many of these basis sets can I form? Well, I can form an infinite number of these basis sets, where each one of these basis set is k over lambda. And what can lambda be? Anything. It can be any wavelength. So essentially, this is a wave traveling this way, this is a wave traveling this way of any wavelength, right? And then what I'm going to do is integrate over every wavelength, every continuous wavelength. Do you see that? So k is our integration variables. So this thing is a wave of, this is a wave that way of wavelength, and it's a wave this way of that wavelength. But then what I'm going to do is I'm going to integrate over every possible wave length with a wave this way and that way.
Negative infinity, positive.
Yeah, I'm going to go 0 to infinity, all right, because the wavelength is positive, all right? But there's some tricks there, so I'm going to go 0 to infinity here. And then what I'm going to say is my real particle is just not, but it's not a finite summation where I'm finding the projection onto this denumerably infinite basis set. I'm finding the probability density on top of this continuously infinite basis set. All right, and this is called the Fourier integral. And by the way, and before when we did a denumerably infinite basis set, our job was to find CNs, right? When we used Fourier's trick. What do you think our job here is going to be? To find these things. And what do you think I'm going to do here?
Fourier's trick.
I'm going to use Fourier's trick for Fourier's integral, and I'm going to solve for the psi ends. All right, and then we'll be done with the free particle. And then I'm going to just do one scattering state problem, and we're done with Chapter 2 on Thursday. All right? Half the stuff, the material for this course is Chapter 1 and Chapter 2. We're done.
And then what's Tuesday?